In Chapter 4, we're going to look at aqueous reactions. So we're going to look at lots of different chemical reactions as they happen in water. As always, there are suggested problems that you can try from the end of the chapter. When we look at chemical reactions, there is a relationship between the amount of our reactants and the products that are formed. And because there's this relationship, it helps us to determine the amounts of all of the other substances in the chemical reaction. And this is because we have the law of conservation of mass. And because we are using our chemical reactions and balancing them and balancing the atoms that are in the chemical reaction. The study of this relationship between our chemical quantities is called stoichiometry. And it sounds like a big complicated word, but essentially what we're doing is just looking at the coefficients in front of our balanced chemical reaction to relate the amount of one substance to a different substance in the chemical reaction. So we're just using coefficients. So if we look at our reaction stoichiometry, we're relating the chemical reaction through those coefficients. So we can think about it either as molecules, so 2 molecules of octane reacting with 25 molecules of oxygen to form 16 molecules of carbon dioxide and 18 molecules of water. But because we know that 6.022 times 10 to the 23rd molecules is a mole, we can also think about this balanced chemical reaction as moles of the substances. And this is much more useful to us in a laboratory setting because we can handle 25 moles of oxygen, but getting 25 molecules of oxygen is not a reasonable thing that we can do in the lab. This also gives us a relationship between each one of these quantities. So if we know the amount of one, we can calculate the amounts of the other. So let's step away from molecules and moles for a minute and focus on something that is maybe a little more relatable. So let's talk about pizzas. Okay? And we know that if we're making pizzas, that there is a recipe that we need to follow, and we have to have a specific amount of ingredients that we can use. So let's say that our recipe is we need 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese to make our pizza. We're not allowed to substitute in ingredients. We're also not allowed to skimp on our ingredients in order to make the pizza. So we can express this mathematically as a ratio. So 1 crust to 5 ounces of sauce to 2 cups of cheese to 1 pizza. So if we want to figure out how many pizzas we can make, we can use the amounts of the different ingredients to help us figure this out. So if we assume we have enough of the other ingredients and we have 6 cups of cheese, we have a relationship that we know that it takes 2 cups of cheese to make a pizza. If we have 6 cups, that means that we can make 3 pizzas. We're canceling our units. This might look familiar, like dimensional analysis. Okay. So let's predict the amounts from our stoichiometry. Okay. We can just look at the amounts of just one substance to figure out the amounts of the rest. So if we want to figure out how much carbon dioxide can be made from 22 moles of octane during our combustion, we're going to set up our chemical reaction. Our ratio, 2 moles of octane gives us 16 moles of carbon dioxide. This becomes a conversion factor in our dimensional analysis. We start with our 22 moles of octane. we want the moles of octane to cancel. So the 2 moles of octane go on the bottom, 16 moles of carbon dioxide go on top, and we figure out that we are making 176 moles of carbon dioxide when 22 moles of octane are burned. All right, your turn to practice. If we are undergoing combustion of 0.1 moles of glucose, how many moles of water are formed? Pause the video and calculate. If we have 0.1 moles of glucose, that's the C6H12O6. We can use the coefficients from our balanced chemical reaction. So 1 mole of glucose to 6 moles of water. And we find that we make 0.6 moles of water. Our glucose cancels, moles of water on top, which is what we're trying to find. Let's take it one step further. Now we want to find the grams of glucose that can be formed from 37.8 grams of carbon dioxide in photosynthesis. You might notice that photosynthesis is the reverse reaction of combustion. We have just flipped the reactants for the products. So let's start with our 37.6 grams of CO2. We have to calculate the molar mass of carbon dioxide, so add the mass of carbon plus 2 times the mass of oxygen. You get 44.01 grams for 1 mole of CO2. Now we had to convert from grams into moles so that we could use our balanced chemical reaction. The way we convert into moles is using molar mass. Now that we're in moles, we can use our stoichiometry, or the coefficients, to convert from moles of carbon dioxide to moles of glucose. And now that we're in moles of glucose, if we want to find grams, again we need the molar mass, but now we need the molar mass of the glucose to go back to grams. So 1 mole and we add up the mass of the carbons plus the mass of the hydrogens plus the mass of the oxygens. We get 180.2 grams of glucose. And we can find that we can turn 37.6 grams of carbon dioxide into 25.8 grams of sugar. Here's a practice problem for you. See if you can determine how many grams of oxygen can be made from the decomposition of 100 grams of lead-4 oxide. Your molar masses are provided in parentheses. Pause the video and determine the mass. If we start with 100 grams of our lead-4 oxide, we have to convert from grams into moles using our molar mass. Now that we are in moles, we can convert from moles of the lead-4 oxide to moles of oxygen using our balanced chemical reaction. The coefficients tell us our ratio. 2 moles of lead 4 oxide to 1 mole of oxygen. Now that we are in moles of oxygen, we need to go back to grams of oxygen. So we're going to use the molar mass of oxygen to get to grams. We want the moles to cancel. So 1 mole goes on the bottom. 32 grams go on top. Multiply across the top. Divide by anything on the bottom. And we see that we get 6.689 grams of oxygen.